the next talk is about some electronics project about fans and strobe lights. And the cool thing about this is that the whole hardware has been assembled at the ZAM and Bits and Bugs in Erlangen. So this is C-Freak. Thank you. Thanks for the introduction. Let's just start right away. This is about a project that has been developed here at the Bits and Bugs, and a few weeks ago a few people have been working with a fan and some measurement devices, and they played around with the strobe effect, and they tried to make this fan appear still. And then I had the idea to automate this and build some electronics that would be able to make this effect real, such that the fan appears still standing. And this should be done without software and without being dependent on the fan speed. So how does such a fan typically look like? Normally we have 7 fan blades. That's true for most of the PC fans, but not all of them, but most of them, they are 7. A fan has also a spin signal pin where you can read back the number of revolutions per second. And if we think about what needs to be done to make this fan appear still standing, and we want to illuminate each fan blade, then we come up with 3.5 light flashes per spin period. The number of 3.5 is a little bit suboptimal for realizing that, and I tried a little bit around. So this is my first experiment. At the very top we see the fan, and at the bottom we see the LED. And the spin frequency signal goes into a block. I want to assume to be a black box for the moment. Then goes to a VCO. And this is a voltage controlled oscillator which converts the voltage into a frequency, and the result should, as we just discussed, be something around the 3.5 times the spin signal. And in the end, the LED should flash very briefly, and thus the fan shall appear still standing. But this does not work that good, because there are some components which have tolerances. There are resistors that have dependency on the environment temperature, and voltage spikes might also appear, and this is a little bit difficult, and for that reason I extended this model. It becomes a little bit more complex. So what do we do here? We begin again with the fan and the spin signal, convert it into a frequency and a voltage, and we go with the signal into a subtractor which compares the two frequencies of these two blocks you see here, and from that difference we determine an error. And this error signal is then fed into a controller which controls the set point for the VCO. So the target is always frequency deviation of both signals, that this deviation is 0. what type of controller we need here, that's a topic we will discuss later. Let's have a brief look at the components we need here. So, this is what an operation amplifier looks like. Who has seen something like that before? Ah, it seems like all of you know that already. So that's the symbol for an operating amplifier. It has two inputs, plus and minus. It has energy consumption, plus and minus, VDD and VSS, and it has one output. So there are different frequencies, different voltages and currents. The input voltage is U plus and U minus, and the input currents I plus and I minus, and we have the outputs, output currency and voltage IA and UA. So what you see here is an ideal operation amplifier, and we need to define a few environmental variables. So we have I plus being 0 and I minus being 0. The second is that the input current is unlimited, so it is an ideal current source. And the third condition is that the output is a multiple of the differences of the input. And the output goes to infinite with the factor going to infinite. So this sounds a little bit abstract, but let's continue with the schematic. This is an impedance converter. We connect the output with the negative input. And we can think about what happens if there is a minimal difference between the plus input and the minus input. Let's say the plus input is a little bit larger than the negative input. Then the operation amplifier will, with its huge amplifying factor, that the output is immediately increased. So U plus equals U minus. As long as there's a small difference, the output will be larger, and this chip is constructed in a way such that there is no cascade effect. So, plus is connected to the input and minus to the output.
Und die Schaltung sorgt quasi dafür, dass hier kein Strom reinfließen muss,
and
aber unendlich Strom rauskommt und die Spannung gleich ist.
The schematic looks like that because we want to make sure that UA and UE are identical.
So, eine kleine Nebenbedingung gibt es hier noch.
There's also a small additional condition. This condition is only true if the output is not overdriven.
Aber bei den folgenden Schaltungen. Jetzt können wir nämlich zum Beispiel in
Let's go to an example where we have a voltage divider at the output, and this looks like that. What happens here? We have a feedback. Even if there is a resistor in the line, we have a feedback, and we want to have U plus equals I minus. And then we have this formula down there. UA must be scaled accordingly such that this equation is true. That's the voltage dividing formula. And UA is always larger than UE by a factor.
And so now we can put in the voltage divider a little bit differently. That brings us to this. That is an inverting amplifier. The approach is the same. We have a negative feedback loop, U plus equals U minus. So we have ground connected to plus. And that means that ground is also present between the two resistors. This is called a virtual ground because effectively here we always have ground, but there is no current flowing to the ground as opposed to a real ground. And this is an advantage for us because we can say that UE is decreased by UA. Because and so if we check that the current going through.
So at the input there is no current. It has to run through R2, and we have to go over the resistor and can calculate back to the voltage, and we can see that UA has to be some negative version of UE, and the concrete factor is determined by the two resistors. In addition, there is UE, which is always loaded with R1. And if you compare this with the previous version, the input was at plus. Are you still with us? Great. Okay, let's continue. Now it's getting a little bit more complicated. Now we have the integrating component. It looks a bit like the inverting amplifier, but instead of the feedback resistor, we now have a capacitor in the feedback loop, and now this whole thing becomes time dependent. Let's start with time 0, and the capacitor is empty. Then we see there is UE over R1 or R, and this determines the current. And if the current is constant, the capacitor will be charged with a constant current. And if you charge the capacitor with a constant current, then the voltage rises in a linear fashion. This way, the input voltage can be integrated. This is a bit abstract. You have to believe this right at the moment. But this means in the end that UA is always an integrated version of UE. If we input a sine wave, then we get a shifted sine wave or a phase shifted sine wave. And so on. R and C determine the amplifying factor this schematic would develop with its integrating, together with its integrating feature. And there is again a virtual mass in the middle by which UE is loaded. What else do we need? So we only have 5 volt and ground, and this is what we see. We don't have negative extra voltage. What do we do here? We connect ground. We have VDD with 5 volts at the very top. And this is an inverting amplifier. Instead, connecting ground to, we connect U ref to plus. and this is about half of VDD, so 2.5 volts. And what happens here is that if we connect 3.5 volts, for example, then we get 2.5 volts here, and what happens at the end, let's say both resistors are equal, then we have a voltage drop of 1 volt here, depending on your ref. The same current goes over here. We have the same drop over R2. So UA is UREF minus 1.5 volt, which means we have a reference voltage about 2.5 volts. Okay, back to our block diagram. Now let's look at each block individually. Let's begin with the VCO. I have this IC, the 74HCT4046. This is a PLL IC with VCO and phase comparators. If you would do it the right way, then we probably could also implement this with just one chip, but it looks a little bit more interesting if we use a VCO. What is this chip capable of? It can generate the whole VCO frequency between a few hertz up until to 1 megahertz, and it just needs one resistor and one capacitor for configuration. And as I told you before, there's one issue. The VCO is not entirely linear, as you can see over there. It varies a little bit. That's a diagram from the datasheet. And the VCC is 4.5 volts. I'm using 5 volts, so that's not too far away. And this diagram shows the behavior of the VCO depending on its input voltage. And beginning with 1 volt, it seems like a little bit linear, but then there is a change a little bit further up, and this would mean that the fan would react in a weird way if we are not doing something against that.
And so now we will get to the black box block of the frequency to voltage conversion. This consists of 2 sub-blocks. Those look like this. One of those is a monoflop. That is a circuit that creates pulses with a specific width in the rising edge of the input voltage. So we have the signal with a changing frequency in the input of the monoflop. And what the monoflop is doing is it creates a pulse frequency with the same frequency. And if we take this pulse frequency and we put it in a low-pass filter, then, it will basically iron the pulses out, and we get a voltage that rises linearly compared to the voltage. Yes? How does the low-pass filter compare to the integrating circuit? Yeah, so the question is, how does the low-pass filter behave compared to the integrator? Did I answer that correctly? Okay. The integrator would here create a linear ramp on every pulse, and then at some point get stuck on the positive supply voltage and get stuck there. Okay. Let's look at both of these blocks in a bit more detail. The monoflop is a 74 HCT 123. It's actually two monoflops with a 16-pin package, or bound in a 16-pin package, which is nice because I need two, one for the VCO and one for the fan. The chip has multiple trigger opportunities. It can trigger on different flanks, and you can deactivate it. I did not need that here. The more important thing is that you can individually change the pulse width. You can change it to different values depending on the size of capacitor that you have available. The low-pass filter is a cell-and-key filter. That is an active filter circuit with a operational amplifier, and what this will do we can see on the next slide. And it is relatively easy to configure because there are pre-made filter design tools, like for example this one that we can see here. And you can give your parameters and it will tell you how to configure your operational amplifier. So let's look at what I set there. First of all, I wanted to have a 3 decibel Chebyshev filter, meaning I don't want a flat curve. I want the frequency to jump with 3 decibel, which in my case is not critical. Even more in my case, it was important that the filter flank rises really. And so the 3 dB Chebyshev filter will give you the strongest version of what the filter designer can give you. In my case, I've optimized this to the largest voltage range because it gives you very nice values to work with. And to estimate the frequencies, we need to look at the rotational speed of the fan, which I've set to 500 between 500 and 2000 rotations per minute. This results in a speed signal frequency from 17 to 76 Hertz and a strobo frequency from 3.5 times the speed signal, resulting in 58 to 233 Hertz. And so we can set in the filter designer to only have certain values from that input, and so the stop bands are not aligned exactly to the real ones. So for the speed signal filter, I wanted the triangle wave to be suppressed a bit. So I've set it to 20 Hertz. That's a little bit too high, so it is dampening the frequency quite a bit. The passband will then be 2 Hertz, and that's the highest you can do with this filter step. The VCO filter, accordingly, will have a bit of a higher frequency, the highest frequency I can get. It doesn't dampen as well with lower rotations, but it's not super relevant because at least here we have high rotation speed, so this is fine. So now we have the voltage for the frequency, and now we can go into the subtraction step. For this, very shortly, this is a subtractor circuit. I will not be going into detail too much on this. Basically, if the difference between those two resistors and the bottom two resistors, you have a relatively simple formula which gives you the ratio of the resistances in this path, which is dependent on the difference between the input voltages. I'm using this for the error detection circuit, and so it will either give you one or the error of the previous circuits. So now we have that. Let's go over to the regulator. The regulator is a PI regulator. P and I stands for proportional integrator, so it consists of two independent regulator paths. You can see that here in the schematics. That is a so-called parallel execution circuit. On the top we have a inverting circuit. And so we can see here that if there is an increase in the frequency difference, there will be a jump in the output. And so this means that if the frequency difference by 1 Hertz, the PI regulator will give you a voltage difference of 1 volt. And this also means that if the error is 0, there will be no control signal, meaning the VCO would stop. That would not be very good. And so this means that we cannot use only the PI regulator, because there always must be an error, because otherwise we have no control voltage. And so we have the I component, that's the integrator from previously. And so what this is doing is that as long there is an error, it will increase the VCO voltage until the error is 0. And so that's what we want to have in the long term, because we want the fan to turn with the same rotation speed visually at all times. So the error must be 0, or should be 0. And so this part in the back here, what this is doing is it adds the two effects together from the regulators, and it will average those out, so that we have the effect that if there is a jump, we will always get a jump in the output voltage, and then it will converge towards 0 later.
So because we have quad op amps, we have to reduce the number of op amps we can use in our schematic. So we can implement a PI regulator with only one op amp. That's a combination of two integrators. And if we would short circuit this, we get an inverting one, and we get the integrating one if in the other case, and both of the voltages have the same effect. So if you get a jump in the input value, we also get the jump at the output. And on the long run, they are integrating up, and that's the circuit I've been using here, and that's why we end up with 4 op amps in total. And last but not least, the high-pass filter or the LED driver. That's not very spectacular. It looks like this. We have two 12 volts and a MOSFET, which turns the LED on and off, and a high-pass filter in the very front. For each rising flank of the VCO signal, we get a pulse through the resistor, and this increases the voltage at the gate, which turns the LED on for a very brief time, and then it goes out again. And falling flank does not change anything. So we have a very small and efficient pulse generator for the LEDs. So we covered everything, and now let's go into practice. The first version looked like this. I've built it on the breadboard, and there are a lot of wires. But the current version looks like this. This is what you see here in the front. Yeah. Thanks for listening, and don't know if you have any time left, but if there are any questions. So please give a warm applause, and thank you for this very nice talk. Unfortunately, we don't have time for questions because we have to do a changeover. But most probably we can talk to you during the event, and have a look and inspect your device. It was always put on the tables down below, so you can look at that there. Thank you.